Dear students, welcome to EPG Pathshala. The module title is Introduction to Continuous Probability Function, is in continuation of the previous module Introduction to Random Variables and its Properties. In that module we already discussed that we have two types of random variable. One is discrete random variable and another is continuous random variable. We already discussed discrete distribution function in our previous module, Introduction to Discrete Probability Functions. In this module we discuss continuous probability distributions like normal, that is very well known distribution that is widely used in various different fields, and another distribution is log normal, and we also discussed rectangular distribution, gamma distribution, beta distribution and exponential distribution. These distributions are very much useful in our practical life, so I emphasize more on these distribution and its properties so that one can understand these distribution in depth and use them in practical life. Let's get started. The main objective of this module is to give an introduction to some widely used continuous distribution. We will also discuss about the different continuous distribution with their properties that will help to differentiate between them. To know in detail about the continuous distribution, mathematical and graphical representation of different types of continuous distribution will be discussed. We are very well known that there are two types of random variables in probability, that is discrete random variable and continuous random variable. We are also much known to the fact that probability distribution is a mathematical expression of values of random variable that have specified probability attached with them under specific laws. If random variable is discrete in nature, then the probability distribution function of variable is known as probability mass function. Discrete random variable has distribution that follows some specific laws, properties, and generally termed as discrete probability distribution. There are some discrete distribution that have the features like probability of occurrence of each event is equal likely, discrete uniform distribution, only two outcomes, that is Bernoulli distribution, etc. The detailed discuss about the discrete distribution is already covered in the module Introduction to Discrete Probability Distributions. On the other hand, if the random variable is continuous, then the probability distribution function of the variable is known as probability density function. Continuous random variable has distribution that follows some specific laws, properties that generally termed as continuous probability distribution. There are some important continuous random variables that we'll discuss in this module. Some of them are uniform distribution, normal distribution, gamma distribution, beta distribution, exponential distribution, Cauchy distribution, etc. Note, the probability of the continuous random variable for a specific value is 0. So the probability of all continuous random variable is calculated in interval. So first we will discuss with normal distribution, that is more widely used distribution is in various fields like environmental sciences and biosciences, etc. Normal distribution is considered as the ruling model among all the continuous probability distribution due to its features and characteristics. It is considered as the important part of the probability theory in statistical analysis due to its features. The normal distribution was discovered by De Moivre, Laplace and Gauss. This is the reason that normal distribution is also known as Laplace distribution and the Gauss distribution. Most of the distribution in probability theory tends to normal distribution when they have large sample size or have sample size greater than 30. If the random variable follow normal distribution, random variable is said to be normally distributed. Normal continuous probability distribution is widely used in social science due to its characteristics. As we already said that when the observation is very large, then by using law of probability, the data can be assumed to follow normal distribution. Hence, the normal distribution will help to extract information from the responses of the respondent in the questionnaire. Normal distribution is also used in linear and nonlinear regression, modeling as the error term. In this model are assumed to follow normal distribution. Normal distribution has a vital role in inferential statistics. Normal distribution is the more widely used distribution in hypothesis testing, estimation and to find out the confidence interval of the parameter. Normal distribution has a wide application in parametric test, investment analysis, market analysis and risk analysis. Biostatistics and environmental sciences are the other areas where normal distribution is widely used. mathematical expression. Let us suppose y is a random variable and y is said to have normal distribution with parameter mu and sigma square, which are the mean and variance respectively. Then the PDF of y is given as f of y with parameter mu and sigma, which is equal to 1 upon sigma under root 2 pi exponential minus half y minus mu upon sigma whole square, where minus infinite in y lies between minus infinity to infinity and mu lies between minus infinity to infinity, and sigma is greater than 0. The mathematical notation for random variable y that follow normal distribution is given as y follow normal distribution with parameter mu and sigma square. So we have another standard normal distribution. The standard normal distribution is a special case of the normal distribution with parameter with mean is equal to 0 and variance equal to 1. As the probability of random variable that lies in an interval AB, that is probability of A is less greater less than y is less than b, can be calculated in an exact manner, because the integration cannot give a closed expression. To find out the probability value of continuous random variable for normal distribution with mean mu and variance sigma square, we have to adopt the following method given below. First is to solve this problem. First we have to transform the normal variable to standard normal variable by subtracting mean value from normal random variable and divide it by standard deviation. Second is then calculate the probability of the standard normal distributed random variable from the table given in the literature. So the mathematical expression is given here as, suppose y is a normal distributed random variable, that is y follow normal distribution with parameter mu and sigma square, where z is equal to y minus mu upon sigma, where z is a standard normal variable with mean 0 and variance 1, that is z follow normal distribution parameter 0 and 1, and the PDF of standard normal variable is given as phi of z, which is equal to 1 upon 2 upon square root of 2 pi exponential minus z square upon 2, where z lies between minus infinite to infinite. So there are some properties of normal distribution, and first property is normal distribution is a limiting case of binomial distribution if sample size is very large, that is n follow infinite, and probability of success is very large, that is p is very small. Second property is normal distribution is a limiting case of Poisson distribution if average outcome is very large, that is lambda tends to infinite. And the third property of normal distribution is that it is a bell-shaped curve and symmetrical distribution about mean. So here we have already discussed that while discussing the properties of skewness, we have mean is equal to median is equal to mode, and we have property that when distribution is bell-shaped curve, then the skewness is equal to 0, and that situation mean is equal to mean, median is equal to mode. So generally we are referring to normal distribution where mean is equal to median is equal to mode always hold. So the fourth property of normal distribution is normal distribution curve does not change the shape of curve if we change the mean, that is if we simply move the position of the curve. And the fifth one is if we change the variance of the normal distribution, that will change the peak of the curve. A smaller variance squashes and the largest variance stretches it. And the sixth property, odd center movement will be 0. Even center movement can be calculated by using this relationship, that is mu 2n is which is equal to 1 into 3 is equal to 5 and so on, it is equal to 2n minus 1 power 2n, where n takes value 1, 2 and so on. Sum of differences of two independent standard normal variable also follow a normal variable using the uniqueness property of homogeneity function. If u and v are the two standard normal variable, so if we have w is equal to u plus v and d is equal to u minus v, then w and d both follow normal distribution with mean 0 and variance 2, that is w and d follow normal distribution parameter 0 and 2. So there are few properties, that is if suppose yi are the normal random variable, so linear combination of random variable follow normal variable, that is summation over ai yi, where summation is over I and I vary from 1 to n, that again follow normal distribution with parameter given here as summation of ai mu I, where summation is over I and I vary from 1 to n, and variance is given as ai square sigma square and summation is over I and I vary from 1 to n. So another property of normal distribution is mgf of the normal variable, that is m of t, it is given as exponential mu t plus 1 upon t square sigma square. So mgf of standard normal variable, which is equal to exponential t square upon 2. So basically, if we have a variable that for normal distribution, so after taking mu is equal to 0, and or you can say after subtracting mean or divided by standard deviation, we get the standard normal distribution. So here the new variable, that is y, that is equal to x minus mu upon sigma for standard normal distribution parameter mu, which is equal to 0, and this variance is equal to 1. So from the MGF we can see that after putting mu is equal to 0 and sigma square is equal to 1, we get the MGF for standard normal distribution as exponential t square upon 2. So this is the first example. Suppose there are 100 environmental studies student study in the Central University, and the probability of for any student require a reference book of statistics from the university library on working day is 0.07. How many copies of the book should be kept in the university library so that the probability may be greater than 0.60, that none of the student who has a requirement for a copy from the library has to come back disappointed. So we have n is equal to 100 and p is equal to 0.07. So we can see that this is case of binomial distribution, but here the sample size is very large and the probability of success is very small. So the random variable follow normal distribution with mean np and variance as npq. We already discussed that normal distribution is a limiting case of binomial distribution, so that mu is equal to np, which is equal to 100 into 0.07, which is coming out to be 7, and sigma square is equal to npq, which is 100 into 0.07 into 0.93, and which is 6.51, and sigma is equal to 2.551. So we want y1, which is probability of y is less than y1, which is greater than 0.60, and where z1 is equal to y1 minus 7 upon 2.551, and probability of z is z is less than z1, which is greater than 0.60. Since by normal curve probability of z lies between 0 to z1, which is greater than 0.10. So from standard normal table, z1 is greater than 0.25 and y1 minus 7 upon 2.551 is greater than 0.25. So y1 is equal to 0.25 into 2.551 plus 7. So here we get the approximate answer as 7.63, which is approximately equal to 8. Hence the library should possess at least 8 copies of the book so that none of the students get disappointed without having any book from the library. Suppose y follow normal distribution parameters 18 and 36. Find the probability of the following thing, that is probability of y is greater than or equal to 40 and probability of y is less than or equal to 40 and probability that y is lie between 0 and 30. So here we have mean is equal to 80 and variance sigma square is equal to 36. So standard deviation is equal to 6 and probability of y is greater than or equal to 40, which is we have to find out. So y here is 40, small y is 40 and z is equal to 40 minus 18 upon 6, which is 3.66. So that means if y follows normal distribution, then standard normal distribution variable z that followed the distribution with parameter 0 and 1. So here that means if we are interested to find out the probability that probability of y is greater than or equal to 40, so which is similar to probability of z greater than 3.66 after subtracting mean and dividing by standard deviation. So from the table we can see that probability of z lies between 0 to 3.66, which is 0.4999. So after subtracting the value 0.5, we get the answer as 0.0001. So similarly we have to we get the value that probability of y is less than or equal to 40, so which is probability of y is less than or 40, which is 1 minus probability of y is greater than or equal to 40, because in continuous case the equality doesn't matter, but in discrete case the equality matters. So here we are taking a continuous case, so it doesn't matter whether you are taking greater than or equal to or less than or equal to, but generally we are taking continuous on the right hand side. So 1 minus 0.0001, so which is equal to 0.9999. Similarly, for if we have to find out probability that y is lie between 0 to 30, so the formula here is probability minus 3 is less than z less than or equal to, which is probability of z lies between minus 3 to 0 and 0 to 2, and probability of z is lies between 0 to 3 and 0 to 2. We get the result as 0.49865 plus 0.4772, which is equal to 0.97585. Now we will discuss another continuous distribution function, that is log normal distribution. A random variable capital Y is said to have log normal distribution if log of Y is normal distributed. Let U is equal to log of Y for normal mu and sigma square for Y is greater than 0. The PDF of the log normal distribution of the random variable Y is given as f of Y, which is 1 upon mu sigma into under 2 pi exponential minus log of u minus mu whole square upon 2 sigma square, and u is greater than 0. The volume of the gas in a petroleum reserve, amount of rainfall, size, distribution of a rainfall, droplets, milk production by cows, all can be modeled with log normal distribution. Log normal distribution is also known as Galton and Cobb-Douglas distribution. There are few properties of log normal distribution. Mean of the log normal distribution is given here as E mu plus 1 upon 2 sigma square, and the variance of log normal distribution is variance of u is equal to 2 mu plus sigma square into E sigma square minus 1. So here example here is where we have Y for a log normal distribution, parameter mean as 5 and variance sigma. So we are what is the value of the probability that Y lies between 400 and 600. So here to find out the probability that Y lies between 400 and 600, we use the CDF, that is if we have the probability that 400 is less than Y is less than 600, which is equal to probability of Y is less than 600 minus probability of Y is less than 400. So first solve the probability that Y is less than 600. So as we know that it is equal to phi of log of 600 minus phi upon 8, and which is equal to phi of minus 0.40, and from the table you can see the value that minus 0.40 is equal to 0.65542. Similarly, you can find out the value of Y is less than 400, which is coming out to be log of phi of log of 400 minus phi upon 8, which is equal to phi of minus 0.299, which is equal to 0.61791. So probability of 400 less than Y is less than 600, which is equal to probability of Y is less than 600 minus probability of Y is less than 400, which is equal to 0.65542 minus 61791, which is equal to 0.03751. Hence the probability value that we derive at the end is 0.03751. Now we discuss another distribution, that is called rectangular distribution. Rectangular distribution or uniform distribution is applicable for both discrete and continuous random variable. In this distribution, all the values that random variable can take in a given interval has an equal probability of occurrence. So discrete uniform distribution is a constant quantity whose PMF depends on the number of integer observations. The probability density function of the uniform distribution is also a constant quantity which depends on the length of the given interval. So the main application of the uniform distribution is the random variable generation as well as p-value. P-value is the value that is used to make conclusion about the acceptance and rejection of the null hypothesis. In case of generating random number from any continuous distribution, first generate the random number from the uniform distribution that has interval that lies between 0 to 1. Then equate the CDF of the particular distribution with generated number from the uniform distribution, and then find the required random number. So the mathematical expression for the rectangular distribution and uniform distribution is given here as: suppose a random variable Y is said to have rectangular distribution over the given interval m and n, that is Y follow uniform distribution with parameter m comma n, or Y follow rectangular distribution parameter m comma n. PDF of the rectangular distribution is given as f of Y, which is equal to 1 upon n minus m, and Y lies between m and n. So cumulative distribution function f of Y is given as f of Y, which is equal to minus infinite to y, f of y t dt. So f of y, which is y minus m upon n minus m. So y here lies between m and n, and f of y, which is equal to 1, where y is greater than equal to n. So the properties of rectangular distribution: mean of the rectangular distribution is given as expectation of y, which is equal to m plus n upon 2. The variance of rectangular distribution is given as variance of y, which is equal to n minus m whole square upon 12. So movement density function is given as m of yt, which is equal to exponential of nt minus exponential of mt divided by t into n minus m. So if y has a uniform distribution that lies between 0 to 1, the distribution of minus 2 log y follow exponential distribution with parameter half. So we have example here that y follow uniform distribution with parameter 820. What is the value of y that lies between 9 to 18, and we were interested in to find out this probability. So we also have to find out the expectation variance. So PDF of the uniform distribution is given as f of y, which is equal to 1 upon n minus m if m y lies between m and n. So after putting the value of n and m, we get the value as 1 upon 20 minus 8, which is equal to 1 by 12. So y lies between 8 to 20. Now calculate the probability. So probability of y that lies between 19 and 18, which is equal to integration 9 to 18, and PDF is given as 1.12 dy. So after solving the integration, we get the result as 9 upon 12, which is equal to 3.4. So mean of the uniformly distributed random variable y is given as expectation of y, which is equal to m plus n upon 2, and expectation of y after putting the value of m and n, we get the result as 14. So variance of the uniformly distributed random variable y is given as variance of y, which is equal to n minus n upon whole square upon 12. So after putting the value n and m, we get 20 minus 8 square upon 12. So variance of y is equal to 12. So average weight gained by a person in winter is uniformly distributed from 0 to 50 lbs, that is pounds. So find the probability that a person will gain weight between 70 to 30 pounds in winter is given by using the distribution function of uniform distribution. So first find the range of the variable on the axis. We know that the area under a probability distribution is always 1. Hence, the random variable x follows uniform distribution with constant probability, that is 1.50. Now find the width of the area, in which we have to find the probability that it lies between 17 and 30. So we have a range that is given as 30, that we have derived after subtracting 17 from 30. Hence the probability of a person gain weight in winter between 17 and 30 is given as 13 into 1 upon 50, that is 0.26. Now we consider another continuous distribution function, that is beta distribution of type 1. Beta is also widely used in different areas. So we discuss this distribution in this module. So beta continuous variable having distribution of type 1 represent a family of probabilities and outcomes for proportions. For example, how likely is that the current Prime Minister of India will win the next Prime Minister election? One of us few thinks that he will win. One of us think that he will not think that some of them he will not win or win. To solve this type of problem, solution beta distribution will be used. Beta distribution of type 1 is also known as basic beta distribution or beta distribution of first kind. There are many applications of the basic beta distribution, like testing of Bayesian hypothesis, the rule of succession, task duration modeling, etc. So the mathematical expression of beta distribution is a random variable y is said to have a beta distribution of first kind with parameter alpha and beta, with y follow beta 1 with parameter alpha beta. The PDF of the beta distribution of first kind is given as f of y, which is equal to 1 upon beta with parameter alpha beta, and which into y power alpha minus 1 and into 1 minus y power beta minus 1, where y lies between 0 and 1 and alpha beta is greater than 0. Now we will discuss the properties of beta distribution of first kind. Mean of the distribution is given here as expectation of y, which is equal to alpha upon alpha plus beta. So variance of the distribution is given as variance of y, which is alpha beta upon alpha plus beta whole square and alpha plus beta plus 1. Harmonic mean of the distribution is given as h is equal to alpha minus 1 upon alpha plus beta minus 1. If alpha is equal to beta is equal to 1, beta distribution of first kind follows uniform distribution with interval 0 to 1. If y follow beta distribution of first kind with parameter alpha beta, and y1 minus y follow beta distribution with parameter beta alpha. Suppose capital Y follow beta distribution parameter alpha and beta, and x is another random variable such that x given y follow beta distribution with parameter n comma y. Then y given x is equal to x follow beta distribution with parameter alpha plus x, beta plus n minus x. Suppose y is a random variable with PDF f of y, which is equal to k into y3 into 1 minus y power 4, where y lies between 0 to 1, where k is a constant. So we are interested to find out the value of k. So the PDF of the beta distribution is given as f of y, which is equal to 1 upon beta alpha beta and into y power alpha minus 1 into 1 minus y power beta minus 1, where y lies between 0 to 1 and alpha beta is greater than 0. So what is a PDF? So PDF of f of y is given as k into y power 3 and into 1 minus y power 4. So y lies between 0 to 1. By comparing of these two PDF, we can see that alpha is equal to 4, beta is equal to 5, k is equal to 1 upon beta alpha beta, and as we know that the value of beta parameter function is gamma alpha gamma beta upon gamma alpha plus beta. So we derive the k value as gamma of n 9 upon gamma of 4 gamma 4 and gamma 5, and gamma here is equal to gamma of x is equal to x minus 1 factorial. So after solving the gammas, we get the result as k is equal to 280. So now we'll discuss another type of beta distribution, that is called beta distribution of second kind. So beta distribution of second kind is also known as beta prime distribution and inverted beta distribution. Beta distribution of second kind is the odd distribution associated with a beta distributed random variable. Same as the basic beta distribution, the beta distribution of second kind is also used to model random probabilities and proportions. The mathematical expression of beta distribution of second kind is a random variable y is said to have beta distribution of second kind with parameter alpha beta, where y follow beta 2 with parameter alpha beta. PDF of the beta distribution of second kind is given as f of y, which is equal to 1 upon beta alpha beta y power alpha minus 1 over 1 plus y power alpha plus 1, where y lie between 0 to infinity and alpha beta is greater than 0. So properties of beta distribution of second kind. Mean of the distribution is given as expectation of y is equal to alpha upon beta minus 1. So variance of the distribution is given as variance of y, which is equal to alpha into alpha plus beta minus 1 divided by beta minus 1 power whole square and beta minus 2. Harmonic mean of the distribution is given as h is equal to alpha minus 1 upon beta. If y follow beta distribution of second kind with parameter alpha beta, then then 1 plus y is equal to 1 upon x, and we after solving the expression we get x is equal to 1 upon 1 plus y that follow beta distribution of first kind with parameter beta alpha. So we have another continuous distribution, that is exponential distribution. A random variable that follow exponential probability distribution is used to describe the time between Poisson point process. Poisson point process is a process in which events occur continuously and independently at a constant average rate. It is also known as memoryless distribution. It is a particular case of gamma distribution. So exponential distribution is not same as the exponential family of the distribution. So exponential distribution has a wide application in reliability, stochastic process, etc. Exponential distribution is the only distribution that has a constant failure rate, so it has a great importance in reliability. Exponential distribution is also used to find inter-arrival time in a homogeneous Poisson process. So exponential distribution is also known as negative exponential distribution. So the mathematical expression for the exponential distribution is given here as let us suppose y is a random variable that follow exponential distribution with parameter alpha. The PDF of the exponential distribution is given here as f of y, which is equal to alpha into exponential minus alpha y, where y is greater than equal to 0, alpha is greater than 0. The CDF is given as f of y, which is equal to 1 minus exponential minus alpha y. And some of the properties of exponential distribution are given here as mean of the distribution is equal to 1 upon alpha, and the variance of the distribution is given as 1 upon alpha square. And if alpha lies between 0 to 1, then variance of y is greater than y is greater than expectation of y. If alpha is equal to 1, then variance of y is equal to expectation of y. If alpha is greater than 1, then variance of y is less than expectation of y. And the last property of exponential distribution is known as a lack of memory property, distribution property. Suppose y is the exponential distribution for every constant state is greater than 0. So if probability of x is less than equal to y, given that y is greater than equal to k, that is equal to probability of y is less than equal to y. That means any events that occur prior that doesn't have any relevance to the current probability. So probability of x is less than equal to y, given that y is greater than k, it is equal to probability of y is less than equal to y. So we have example here, that is, on the average a certain machine parts last for 10 years. The length of the time the machine parts last is exponential distributed. What is the probability that machine part less than more than 8 years? So let y is the span of the time in years a machine part lasts. So mean is given as 10. So alpha is equal to 1 upon mu, which is equal to 0.10. So if we have to find the probability that y is greater than 8, so for that probability of y is greater than 8 can be written as 1 minus probability of y is less than 8. So which is equal to exponential of minus alpha y, and after putting the value of y and alpha, we get the result as 2.22. So it means the probability that machine part less than more than 8 years is 2.22. So we have another continuous distribution, that is gamma distribution, that is a generalization of exponential distribution. Gamma distribution is widely used distribution like normal distribution, exponential distribution. Gamma distribution is also related to the beta distribution. Problem can be seen in practical situation related to gamma distribution in process where the waiting time for more than 1% between Poisson process. Suppose random variable y is said to follow gamma distribution with 1 or 2 parameters. The mathematical expression for the PDF of gamma distribution is given as, if y follow gamma distribution with parameter alpha beta, 2 parameter gamma distribution is given as f of y, which is equal to beta power alpha e power minus beta y, y power alpha minus 1 divided by gamma alpha, and with y alpha beta is greater than 0. If y follow gamma distribution parameter alpha 1, one parameter gamma distribution is given as f of y e power minus y alpha minus 1 divided by gamma alpha. So the sum of the properties of gamma distribution are given here as, mean of the gamma distribution is given as, for 2 parameter case it is equal to expectation of y, which is equal to alpha upon beta. For 1 parameter case, expectation of y, which is equal to alpha. So variance of the gamma distribution is given as, for 2 parameter case we have variance of y, which is equal to alpha upon beta square. For 1 parameter case, variance of y is equal to alpha. So moment density function is given here as m of yt, which is equal to 1 minus t power minus alpha, and where mod of t is lie between 1. So some of the properties that represent the relationship between gamma distribution and Poisson distribution are given here as, Poisson distribution and 1 parameter gamma distribution have same mean and variance. So 2 parameter gamma distribution variance is less than mean. So another property is gamma distribution tend to normal distribution as indefinite large values of parameter alpha. So gamma distribution follows additive property. Suppose that y, capital Y1, capital Y2 and so on yn are n gamma variable with 1 parameter alpha 1, alpha 2, alpha n, then additive property of n random variable is given as summation of yi, where summation is over I and I vary from 1 to n, that follow gamma distribution with parameter summation of alpha I, where summation is over I and I vary from 1 to n, comma 1. So if x follow gamma distribution with parameter alpha 1, then and y follow gamma distribution with parameter alpha beta comma 1 are 2 independently gamma variates, then x upon y that follow another distribution, that is beta distribution of second kind with parameter alpha beta. If x follow gamma distribution with parameter alpha 1 and y follow gamma distribution parameter beta 1 are 2 independently gamma variable, then x upon x plus y follow beta distribution of first kind with parameter alpha beta. Now we will discuss how gamma distribution is related with chi-square distribution. Gamma distribution is related with chi-square distribution, or we can say that for specific values of the parameters of gamma distribution, gamma distribution can be transformed into chi-square distribution. Let us suppose if we take alpha is equal to mu by 2 and where mu is a positive integer and beta is equal to 1 upon 2, then the PDF of the chi-square distribution is given as f of y, which is equal to 1 upon 2 power mu by 2 into y mu by 2 minus 1 into e minus y upon 2 divided by gamma of mu by 2 for all y is greater than 0. And movements of chi-squares are given as mean of the chi-square is equal to mu and variance is equal to 2 mu, and mg of is equal to 1 minus 2t power minus mu by t. If y follow gamma distribution parameter alpha beta, then 2 beta w has a chi-square distribution with parameter 2 alpha that has 2 alpha degree of freedom. That is the important result that has a great practical importance. We can directly calculate the probability of gamma distribution from chi-square table by transformation. So here we have an example here. So if y follow gamma distribution with parameter 2, 1.5, then calculate the probability that probability of y is greater than 4. So since y follow gamma distribution with parameter 2, 1.5, we know that 3y follow chi-square distribution with parameter 4. So probability of y is greater than 4, which is equal to probability of 3y is greater than 12, and probability of chi-square with parameter 2 alpha, which is greater than 12. So using the chi-square table, the value of probability of chi-square 4 is less than equal to 12, which is equal to 0.9826. So probability of y is greater than 4 is equal to 1 minus 0.9826, which is 0.0174. So we have another continuous distribution, that is Cauchy distribution. Cauchy distribution is continuous probability distribution, and Cauchy distribution is named on the French mathematician and physicist Augustin Cauchy. Cauchy distribution is also known as Lorentz-Cauchy-Lorentz distribution. Cauchy distribution does not have finite moments like mean, variance and moment density function. So median and mode and median of the Cauchy distribution are well defined. Cauchy distribution found in the field of working with exponential growth. So let us suppose y is a random variable and y is said to follow Cauchy distribution with parameter pi, with scale parameter s and location parameter t. If the PDF is given as f of y, which is equal to 1 upon s pi 1 plus y minus t upon s whole square. So if t is equal to 0 and s is equal to 1, Cauchy distribution is known as standard Cauchy distribution. The PDF of the standard Cauchy distribution is given as f of y, which is equal to 1 upon pi into 1 plus y square, and y lies between minus infinite to infinite. The curve of the standard Cauchy distribution will be same as the standard normal distribution bell-shaped curve, but there are some properties of Cauchy distribution. These are mean variance, coefficient of variation, and kurtosis are undefined. Mode and median will be location parameter t, and skewness is equal to 0. In the end, I would like to conclude this module. In this module, we discussed different continuous probability distribution. First, we discussed normal distribution, and after that, we discussed standard normal distribution. We already discussed that how one can derive standard normal distribution from a normal distribution. After that, we discussed log normal distribution and their relationship between log normal distribution and normal distribution. After that, we discussed rectangular distribution or uniform continuous distribution, and we can see that how we can use this distribution in practical life. After that, we discussed beta distribution of first kind, beta distribution of second kind, Cauchy distribution, exponential distribution, gamma distribution. In this module, we try to understand that how these distributions are related with one another, so that one can understand that which distribution we can use in which particular situation. Hope you enjoyed the module very well. Thank you.